Good morning, students. So let me continue with induction motors. Okay. So in the previous class, we studied about the construction of induction motor, right? And induction motors are of two types, and the classification is done based on the rotor construction. So the two types of three-phase induction motors are squirrel cage induction motor and slip ring induction motor. Squirrel cage induction motors have a fixed resistance rotor, and due to which the speed cannot be varied. So the squirrel cage induction motors are used in constant speed applications such as blowers, fans, drilling machines, etc., etc. On the other hand, in case of slip ring induction motor, you have a provision to insert external resistance into the circuit. So due to which you can vary the rotor resistance. By varying the rotor resistance, you will be able to vary the speed. Hence, the slip ring induction motors can be used in variable speed applications, such as electric vehicles, trains, lifts, hoists, etc. All right. So that was about the constructional aspects and the applications of the two types of induction motors. Now, today, let us look at one very important concept, something known as rotating magnetic field. Rotating magnetic field. Okay. Now, the induction motor, based on the supply, can also be classified into two types: single-phase induction motors and three-phase induction motors. The biggest difference between the single-phase induction motors and three-phase induction motors is the rotating magnetic field. In short, it is called as R.M.F, rotating magnetic field. So, the single-phase induction motors are not self-starting. Are not self-starting. On the other hand, the three-phase induction motors are self-starting. Self-starting. Okay. Now, what do you mean by this non-self-starting or self-starting? Okay. Self-starting in the sense, the moment when you connect a motor to an electric supply, the motor should start rotating. That is what is known as self-starting. Now, it is observed that if you consider a three-phase induction motor, and if you connect the stator winding of three-phase induction motor to a three-phase AC supply, the motor gets into motion. So that means to say the motor starts automatically. Okay. On the other hand, if you connect single-phase AC supply to a single-phase induction motor, the single-phase induction motor will not start. And that is something to do with the magnetic field. So the single-phase induction motor doesn't have self-starting capability. That's because the magnetic field produced in single-phase induction motor is not rotating in nature. Instead, it is pulsating in nature. So magnetic field is pulsating. So pulsating magnetic field doesn't produce any useful mechanical rotation. So that is the major difference between the single-phase induction motor and three-phase induction motor. Now, having said that, that is the single-phase induction motor is consisting of pulsating magnetic field. The three-phase induction motor, okay, produces something known as rotating magnetic field. rotating magnetic field. And this rotating magnetic field, the speed of rotating magnetic field is usually denoted by Ns, and Ns is given as 120 F by Q. The same relation you have used in case of alternator. Okay, so Ns is equal to 120 F by Q. Okay, now it is not actually included in the syllabus. Now, since you are from electrical branch, I thought I'll just throw some light on this pulsating magnetic field. Okay. Now, what happens in case of single phase induction motor is that the moment when you connect the supply voltage to a single phase induction motor. Okay, can you give me an example for single phase induction motor? Ceiling fan. Ceiling fan is a perfect example for single phase induction motor. I don't know how many of you have seen. Sometimes what happens is that even after connecting the ceiling fan to a single phase AC supply, you must have observed this. The ceiling fan simply fails to rotate. That is due to the pulsating magnetic field. So that is the reason the ceiling fans are always used, in combination with a capacitor. So capacitor basically acts like a starter or starting mechanism. All right. So you need a capacitor in order to start a single phase induction motor. On the other hand, your three-phase induction motor doesn't require a capacitor. Just if you connect a three-phase AC supply, the motor simply starts. All right. So that is the reason, in your house ceiling fan, you will find a capacitor connected to the ceiling fan motor. Okay. Now, single phase AC, this is how you represent, right? One positive half cycle and one negative half cycle. So this single phase voltage, okay, when it is connected to the stator winding, produces single phase current, and the single phase current produces alternating flux. Okay, let's say this is your flux with respect to time. So single phase voltage will establish single phase flux in the winding. Now you can clearly observe that the flux wave will have one positive half cycle and one negative half cycle in a particular cycle. Now, when the flux wave is positive bound, what happens is that the positive half of the flux wave produces something known as forward rotating torque. Forward rotating torque. After pi by 2 interval, what happens? The direction of flux wave changes. So when the direction of flux wave changes, what will happen? The current flows in reverse direction, due to which the negative half of the flux wave gives, any guesses? The backward rotating torque. Backward rotating torque. And this process continues one cycle after the other. So whenever the motor is experiencing, encountering the positive half cycle of the flux, the motor tries to rotate in forward direction. The moment when the negative half cycle of the flux comes into picture, the motor tries to rotate in the backward direction. So what is happening effectively? The motor tries to move in forward as well as backward direction. So what about the net rotation? Net rotation is 0. That is called as pulsating magnetic field. And the pulsating magnetic field will give rise to pulsating torque. And pulsating torque is of no use because it cannot impart any mechanical motion to the motor. Okay, so that's the reason all single phase motors are used along with capacitors. So this capacitors basically serves as the starters or starting mechanism for the induction motors, and they are widely used in ceiling fans as well. All right. So that is about the pulsating torque and the non-static capability of single-phase induction motor. However, in three-phase induction motor, you do not have a single waveform, right? You have three wave voltages. You have voltage for R winding, Y winding, and B winding. So due to which, what happens is that the due to the three voltages, what happens is that okay, mathematically we are going to prove also the resultant flux. Okay, resultant flux phi r is not zero. On the other hand, you can say the resultant flux, okay, phi r is something like zero. That's the reason there is no torque produced in single phase induction motor. So resultant flux is not easy. I mean, it is not equal to zero. Instead, in case of three phase induction motor, the resultant flux is something like 1.5 times the maximum value. Okay. Due to this condition, the three-phase induction motor is self-starting in nature. Okay. Now, in detail, let us look at why do we get the resultant flux value as 1.5 times the maximum flux. All right. So that is nothing but a concept of rotating magnetic field. All right. So this rotating magnetic field concept is very, very important from exam point of view. All right. Okay. Fine. Now, to understand the concept of rotating magnetic field, let us draw the simple induction motor diagram. Okay. Assume that you have a stator, okay, and the stator is connected with three windings: R winding, Y winding, and B winding. Okay. And the three-phase winding is then connected to a three-phase supply. The three-phase winding is connected to three-phase supply. And this is your stator. Okay, and this is your rotor. Okay, this is your rotor. The gap between stator and rotor is called as air gap. Gap between stator and rotor is called as the air gap. Okay. Now, in case of three-phase induction motor, okay, motor requires power input as electrical power, right? The moment three-phase AC supply is connected, what happens is that a rotating magnetic field rotating at Ns is equal to 120 F by P is produced. And this rotating magnetic field rotates in the air gap. Let's say in the air gap, it rotates something like this. This is just the visualization. Okay. Because this magnetic field is not stationary, it rotates in space. Okay. So this is how the rotating magnetic field rotates in space. Okay. Due to which there will be a magnetic, due to mutual induction, there will be an induced EMF, and that EMF will produce torque, and the rotor starts rotating. The working principle sometime later, let us consider. All right. Now, since the supply is balanced in nature, okay, the flux produced in the three winding is also balanced. So let us say the flux produced in R winding, phi R, flux produced in Y winding, phi B, and flux produced in B winding, let us say phi B. Okay. So as the supply system is balanced, the flux produced in the three windings will also be balanced. In the sense, phi R can be written as phi M
sine omega t, equation 1. Phi m sine of omega t minus 120, equation 2. Phi m sine of omega t minus 240 degree, equation 3.
Now, the resultant flux, okay, since R I have already used to represent the flux induced in R winding, let us call phi Re as the resultant flux. The resultant flux phi Re is basically the vector sum of phi R, phi Y, and phi B. Right? You have to resolve the three vectors in order to find the resultant flux. Okay. Now, to find an expression for resultant flux, what we can do is we can consider different intervals of time. Okay. So let's consider omega t as say 0 degree, 60, 120, 180. So for example, let's consider half cycle duration. Okay. So you can write that something like, let us evaluate phi Re over a half cycle. Let us evaluate phi Re over a half cycle. That is omega t equal to, let's say, 0 degree, 60 degree, 120 degree, and 180 degree. So if you can carry out the analysis for one half cycle, that's more than sufficient, okay? Because sine wave is a symmetrical waveform. So what happens in positive half cycle is going to happen in the negative half cycle as well. All right, fine. So case 1, let us consider. So in case 1, let us consider, okay, put omega t equal to 0 in equation 1, comma 2, comma 3. So put omega t equal to 0 in equation 1, 2, and 3. So what do you get? Phi r as? You will get phi r is equal to phi m sine of omega t. And what are you putting omega t as? 0 degree. So sine 0. So sine 0 is 0. So you will get phi r is equal to 0. Okay. Let's see what you get as phi y. So phi y is equal to phi m sine of omega t minus 120 degree. So sine minus 120 degree. Okay. So what do you get? Sine minus 120 degree as minus root 3 by 2 phi m. Phi m. And finally, you can find out phi b. So phi b is equal to phi m sine of omega t, which is 0. So minus 240. Okay. So phi m sine of minus 240 degree. Sine minus 240 is plus root 3 by 2. Phi m. So this is what we get when we substitute omega t equal to 0. All right. So we have found the values of phi r, phi y, and phi b by substituting omega t value. Okay. But in order to find out phi re, what is that you should do? You should vectorically add phi r, phi y, and phi b. So let's go for vector addition. Okay. As usual, we have already seen this technique in three-phase AC circuit. Okay. So what you can do is you can draw, let's say, R axis, Y axis, and B axis. B axis, such that the angles are 120 degree from one another. 120, 120, and 120. Okay. Now, after drawing these axes, what you can do is you can start projecting the corresponding vector values. What about the value of phi r? Phi r is 0. Okay. So 0 means there is no length and there is no direction. Okay, you can just discard this particular vector. What about phi y? Phi y, we have the value of phi y as minus root 3 by 2. All right. Now, this is the positive direction of y-axis. But what is that we have got in our equation? The negative value. So you have to project the vector in opposite direction. So let's project phi y. Let's call this as phi y. Okay. I hope you are understanding. Negative sign is there. Hence, you have to project the y-axis in the opposite direction. And this length phi y refers to the value of phi y, which is root 3 by 2 phi. All right, fine. Next, you go for phi b. And what is phi b? Phi b is plus root 3 by 2 phi m. Okay. So the positive axis of b is already present. So we'll have to just mark phi b. Okay. And if you resolve phi b and phi a, you will get the resultant value phi r e. Let me just erase this part so that we get some space. Okay. All right. Let us resolve the vectors. Okay, you know, right? Taking this as the reference, you have to project this vector such that the line is parallel. And similarly, taking this as reference, you have to project this vector. So somewhere here, the two vectors are going to intersect, and the resultant is given by the diagonal. Okay, so this diagonal basically gives phi r e, the resultant value. All right. Once you have phi r e, you can find out the resultant value by, say, drawing a perpendicular bisector. Let's say this is origin O, this is A, this is B, and this is C. And this is your angle theta. This small angle is angle theta. Okay. So you can write down here itself and write cos theta. Okay, cos theta is equal to adjacent by hypotenuse. So adjacent is OC, and hypotenuse is OB. Oh. Now, can anyone tell me what is this theta? So between R and B, what is the angle? Between R and B, it is 120 degrees. Right? Between R and B, it is 120 degrees. Now, between R and phi r e, what is the angle? 60 degrees. 60 degrees. So the angle between phi b and phi r e is basically 30 degrees. So theta is 30. Theta is 30. So cos 30 is root 3 by 2. So root 3 by 2 is equal to OC. Okay. Now OC can be written in terms of the diagonal, right? OC can be written as half of OA. So OC can be written as OA divided by 2 into OB. Okay. Now length OA is equal to phi r e divided by 2 into OB. Length OB is equal to what? Phi b. And what is the value of phi b? It is root 3 by 2 phi m. So root 3 by 2 phi m. Or you can write root 3 by 2 is equal to phi r e
divided by phi m into root 3. That implies when you cross multiply, what do you get? Phi m. Okay, it's okay. I will add it up properly. So when you cross multiply, 2 gets cancelled. You will get root 3 into root 3 phi m divided by 2 is equal to pi r e, or pi r e is equal to root 3 into root 3 is 3 by 2 into phi m, or 3 by 2 is 1.5 into phi m. So this shows that for a three-phase system, the resultant flux is not 0. The resultant flux is 1.5 times the maximum flux value. Okay. So this is for case 1, wherein we took omega t equal to 0. The similar analysis you need to carry out for other values of omega t. All right. Now let us consider case B. Okay. So in case B, we shall put omega t equal to 60 degree in equation 1 to 3. In equation 1, 2, 3. Okay. You tell me now, what do you get? Phi r. I don't have the equations because I have erased. Probably you have written those equations in your notebook. So phi r is equal to phi m sine omega t, so sine 60. Okay. So that's root 3 by 2. Fine. Okay. Next you have phi y. Phi y is equal to phi m sine of omega t minus 120 degree. So it is 60 minus 120 degree. Okay. So that's sine of minus 60. And that is minus root 3 by 2. And phi b. So phi b is phi m sine of omega t minus 240 degree. Okay. So 240 minus 60 is 180. Sine 180 is 0. So you'll get phi b is equal to 0. Okay. So let's find phi r e by resolving the three vectors. Okay. The same process. R axis, y axis, and b axis. Okay. Now along phi r, do we have anything? Yes, we have positive value, that is root 3 by 2. So let's project that vector. So this is our phi r. Okay. Along phi y, what do we have? We have minus root 3 by 2. So positive direction of y is here. So project the vector in opposite direction. Okay. So this is your phi y. And along phi b, you don't have anything because the value is 0. Okay. Now, when you resolve phi r and phi y, you will get the resultant value. Okay. So how will you resolve? The same process? Taking this as the reference, let us draw a line parallel. Okay. Similarly, taking this as reference, let us draw another line parallel. Okay. So here it intersects. So this is your resultant. This resultant can be taken as phi r e. Okay. And you can draw, say this is O, this is A, this is B, and let's say the bisector is line BC. So line BC is your bisector, and you are interested in finding out this angle. So this angle is nothing but 30 degree. Okay, and then you try to find out cos 30 degree. Okay, so from which triangle? From right angle triangle. Okay. From the right angle triangle OCD. Okay. If you are not able to figure out which triangle I am taking, I have written the triangle, right angle triangle OCB. So cos 30 is equal to adjacent by hypotenuse. So this is your adjacent OC, and hypotenuse is OB. So this OC can be written as half of OA. Length OC is half of length OA. So it is OA divided by 2 into OB. OB represents phi r. And what is phi r? Phi r is root 3 by 2. Okay, we'll write it as OB and then we will substitute the value. So OA represents phi r e divided by 2 into OB. OB is phi r and phi r is root 3 by 2. Okay, into phi r. So 2 gets cancelled and then you cross multiply. So what is cos 30? Cos 30 is root 3 by 2, which is equal to resultant value phi r e, and which is divided by, root 3 into phi m, or when you cross multiply, you will get phi r e is equal to 1.5 times phi m. Okay. Okay. So what is happening basically? Can anyone tell me? So you took omega t as 0 degree, and then you took omega t is equal to 60 degrees. So what is happening is the resultant value is remaining the same. The resultant value, you are getting it as 1.5 times phi m. Okay. But you please look at the direction of the resultant vector. In the first case, the direction of the resultant vector was vertically upwards. Now the direction is being, tilted to the right hand side direction. So when you consider omega t equal to 120, you would see that the magnitude of phi r e remains the same, but the direction keeps changing. So probably for omega t equal to 120, you may have your resultant phi r e somewhere here. And when you take omega t equal to 180, your direction will be somewhere here. Okay. So the remaining two cases we have to look into now. All right, let's see, are we getting this direction or not? So with that direction, you can say that the magnetic field is rotating in nature. That's because the resultant keeps on rotating in space. Since the resultant is rotating in space, we call it as rotating magnetic field. Okay. Try out with case C. Okay. In case C, what you can do is you can put omega t is equal to 120. Okay, I'll just go and fetch a pen. So in the meantime, you guys can do it. Omega t equal to okay. All right. So what do you get when you substitute omega t equal to 120 degree? Phi m sine of 120 degree
So sine 120 is positive value. So it is
√3/2 pi m.
and then you substitute 120 in the second equation. So sine of 120 degree minus 120 degree. So that is 0. And in the third one, 120 minus 240, that is minus 120. Minus 120, sine minus 120 is minus √3/2 pi m. Okay. And accordingly, you can redo the vector diagram, the resulting vector diagram. Okay. So I had already given my prediction in the beginning, right? That I should have my resultant somewhere here. Let's see whether we are getting it or not. So phi r is √3/2. Okay. And phi y is 0. So we don't have to touch y-axis. Phi b is minus √3/2. So positive direction is here. So you want the negative value. So you project the vector in the opposite direction. Okay, so let's project something like this. And let's take it as phi b. Phi b. Okay. And now you resolve the vectors. Okay. This is your phi r, and this is your r axis. This is your resultant vector, phi r e. And say this is C, B, and A. This is 30 degree. So from the right angle triangle, OC, A, okay, I'm slightly interchanged, doesn't matter. OCA, cos 30 degree is equal to adjacent by hypotenuse. Okay. OC is half of OB. Okay. And here, into OE. OE. Okay. OB represents phi re divided by 2 into OA. OA represents phi r. And what is phi r? √3/2. So √3/2 phi r. So when you simplify, you will once again get phi r e as 1.5 times phi r. And you look at the resultant vector. The resultant vector, as predicted, it is in the third quadrant now, right? So that's what we were doing the prediction. So similarly, you can do the last case, case D, wherein you put omega t equal to 180 degree. So when you put omega t equal to 180 degree, you will get sine 180 degree. Sine 180 is 0. So flux value along r axis is 0 for case 3. And here what do you get? 180 minus 120. So you will get sine plus 60 degree. So sine plus 60 degree is plus √3/2 pi m. And here you have 180 minus 240, that is sine minus 180 degree. So sine minus 180 degree is minus √3/2 pi m. Okay. And you construct the parallelogram to find out the resultant. So what I will do, I'll construct the parallelogram here itself. Okay. Now, what is phi y? Phi y is √3/2, and I have the positive direction of y here. So I'll just draw phi y. Okay. So this is my phi y. Okay. And phi b phi b, what is it? Minus root 3 by 2. I have already drawn, right, phi b, so I don't have to draw it again. And I have phi y here, phi b here, so you have to find the resultant now. So you can just find the resultant. Okay. Phi r b. Okay. And let's say this is O, B, A, and C. Okay. So this angle is 30 degree. This angle is 30 degree. So you can say that from the right angle triangle, and this is perpendicular, right? Right angle triangle, OCA, cos 30 is equal to adjacent is OC divided by hypotenuse is OA, and same thing. You will get phi r e as 1.5 times phi r. Okay. Now, what is the conclusion? The conclusion is that no matter what value of omega t you take, the resultant value of flux remains the same. So for a three-phase system, the resultant flux remains the same at 1.5 times phi r. Now, what happens to the resultant? The resultant keeps on rotating in the clockwise, in the clockwise direction. Okay. So you can sum up by stating that whenever a three-phase AC is connected to the stator winding of an induction motor, a rotating magnetic field rotating at synchronous speed is produced. The resultant value of rotating magnetic field is 1.5 times phi m, and the resultant keeps on rotating in clockwise direction. Okay, so that is the summary of rotating magnetic field. Okay, now this phenomenon you cannot find it in a single phase induction motor. That's because in case of single phase induction motor, the magnetic field which is produced is fluctuating in nature. Okay, so that completes rotating magnetic field portion. All right. So what I will do, I will take a break here. Okay. So in the next class, let us look at the working of three-phase induction motor and the associated elementary derivations. All right. Thank you so much.